because there's a mutual conductor coupling between the conductors IA, IB. So because of that mutual coupling, then we consider that the impedance between any of the two phase conductors AB, AC, and CA is what is ZAB, while that of the between any of the conductors and the neutral conductors is ZAN. So ZA is between A, B, and C mutually respectively impedance between any of the two conductors, whereas that between neutral conductor and any other conductor is ZAN. We have seen that, and we have already talked about it last time. See here, impedance is ZAB is assumed between each pair. That means between AB, AC, and that is between AB, AC, and AB. So this will be ZAB itself. And between any neutral conductor and a phase conductor, it will be ZAN. So next is, let's say next, what we'll be talking about next is the voltages induced in phase. So now we will see what if current will flow in the phase A, that will induce the voltage in the adjacent phases that we have already talked about. So the voltages induced in phase A, for example, let's say voltage induced in the phase A, for example, by currents in other two phases and neutral conductor. Neutral conductor, they will be shown as sources. That means they will be shown as voltage sources in the loop, as in figure B. So you can have a look at this figure. So let's suppose I am considering a voltage in a phase A by the currents, by which currents in the other phases and the neutral, because there is a B phase, C phase, and a neutral. So currents will be flowing in those phases. So let us say I am considering this loop formed by a line A and a neutral conductor. Now what will happen? Let's say current IA is flowing. So because of the other currents IB, IC, and IN, the voltages will be induced. They will be treated as a voltage. Impedance into currents is voltage. Mutual impedance. Mutual impedance is ZAB. ZAB into IB. ZAB into IC. Because of the neutral, what is the mutual impedance? That is ZAN. ZAN into IN. Then after that will be the self impedance of the phase number A, that will be ZA. After that we have VA dash, N dash, and after that again we'll move to the return conductor because it's an unbalanced condition. ZNN will be there. So ZAN IC. Then because of the neutral conductors, because current is flowing here also, the neutral conductor has a mutual impedance of Zn. So each phase will have now voltage also, ZAN IC, ZAN IB, ZAN IA, and that is a current IN flowing. I'll be repeating, this is a very important point. Now, what we are considering here, we are considering a phase A. When we are considering a phase A, then current flowing through the phase A is IA. So because of the currents flowing in the other phase, because of the current flowing in the other phases are B and C, and there is a neutral conductor. So voltage will be induced. So that voltage will be mutual impedance multiplied by that current. So this is very clear here. So you can see here, this is a ZAB and IB. So phase B has been considered because that will be treated as a voltage source. ZAB IC, phase C. Now neutral has its mutual impedance of ZAN, ZAN IN. Self impedance in the phase A is ZA. ZA has been considered. Now Because neutral conductor will come into the play because there's an unbalanced condition, so current will flow through the neutral conductor. Because of the current in the adjacent phases, the voltages will be induced. So that will be ZAN IC, ZAN IB, ZAN IA, and ZNN is the self impedance of the neutral conductor, and current is IN. So it should be very clear. From this side it is VA dash N dash, and this side it is VAN. So we are forming a loop formed by a line A and a neutral conductor. So that's very clear now here. So the voltage induced in phase A. So for example, we are considering phase A. The voltage is induced because of the two phases and the neutral conductor are shown in this figure number B. So let us apply the Kirchhoff's voltage law now in order to get these values. Applying KVL to loop in figure B. So we'll apply a KVL. Now you can see here, very simple KVL is there. This voltage will be equal to this voltage plus this voltage plus this voltage, all this, but there will be a negative sign on this side. This will be positive, this will be negative, very clearly. So I'll be writing, I think this is not a problem. So VAN can be written as, so first it will be ZAA self impedance, then we'll consider the mutual, ZAB IB, then ZAB IC, okay, then we have with neutral conductor ZAN IN, and then we will move to VA dash N dash. You can very clearly see here. So ZAA IA first positive sign will take, then ZAB IB, ZAB IC, ZAN IN, then here also positive sign, VA dash N dash, that's a positive sign. So now moving to this side, we will have negative signs now. We will have negative signs now. You can clearly see minus ZNN IN plus, I am writing a complete negative sign as ZAN because the neutral conductor, mutual impedance is ZAN IC plus ZAN IB plus ZAN IA. So that completes the first, this loop. Others we will just simplify a bit. We can write this VA dash N dash, we can take on this side. So VAN minus VA dash N dash can be written as, so we'll consider A now. Wherever the A is, we'll take the common. So ZAA minus ZAN IA. Current IA will take common, ZAA minus ZAN, and that will be multiplied by IA. Then second will be, let's consider ZAB now. With IB, ZAB minus ZAN, ZAB minus ZAN IB. Okay, then, oh sorry, just a second, because we have more here. See, ZAB is here, IB, and ZAB is with IC also. So we have to write it. We can write what we can write here. We can write ZAB minus ZAN, that will be multiplied by IB plus IC. Multiplied by IB, because very clear. We will get one term as ZAB IB, sorry, ZAB minus ZAN IB. Out of this we can take IB common. Similarly, we can get ZAB minus ZAN IC. So both we can take commons, and IB plus IC we can write. It's very clear. Next, then third, what we have, plus we can write with ZAN, ZAN minus ZNN. See, here we have ZAN and here we have ZNN. We can take IN common. ZNN, IN. So let's write this equation number 2. So it's very clear, we are just taking the common terms, nothing else. So other equations, other loops, we have to write similarly. We can't derive them. We can write similarly. So what we can write for them, looking at the above equation, we can write them VBN is VB dash N dash. That will be equal to ZAA minus ZAN IB. Then it will be ZAB minus ZAN I A plus IC, and then finally we can write plus, looking at the above equation, similarly we have to ZAN minus ZNN into IN. So let's call it equation number 3rd. Similarly, we can write another equation. This set we'll call 3rd. VCN minus VC dash N dash will be again same thing. We have to write, just manipulate it with ZAN minus ZAN, and this will be IC now. Sorry. Plus ZAB minus ZAN. This time it will be IA plus IB, plus C will be missing now. And final will be ZAN minus ZNN, that will be IN itself. So let's call this set as equation 3rd. Yes, sorry. Beta Sana, it is clear or not up to here?
Yes, sir.
Okay, let's move further. Now what we have, when the line currents IA, IB, IC return together, because now these currents are what? Now these currents are unbalanced currents. So when they will return together as IN in the neutral conductor, we can write it return together as IN. Now because unbalanced conditions are there, so IN will come into the picture. IN in the neutral conductor. In the neutral conductor, so what's going to happen? IN will become minus summation of this IA plus IB plus IC. So let's call it equation number 4. Now substituting the equation set of 2 and 3, substituting the value of IN in equation 2 and 3. Okay. So what we are going to get, let's see. Just we have to replace the values of IN because we want everything in terms of IA, IB, and IC. That's all. So we will have VAN minus VA dash N dash. That will be, we had what here? We had ZA's minus ZAN. So here we had IA, that will remain as it is, plus ZAB minus ZAN. We have IB plus IC. That's not also going to change. That will be same. Minus we had ZAN. Yes, just a second. ZAN. ZAN. That is going to become plus, I think. Yeah. Minus ZAN. And that will be ZAN, and that will be ZNN. That should be multiplied with minus, that will be replaced by IB plus IC. Okay, can make a bracket here. Just a second, I want to check this. ZNN minus ZAN, that will be IB plus IC. This is positive here, so this will become, yeah, this is clear. So if we take this positive, no problem, we can make it negative, then it will become what? ZNN minus, it's one and the same thing. So it doesn't matter, it's not a problem at all. So we can make it negative here one time. Here we can make it negative. Take it positive here. This sign I am taking negative because this is in multiplication. Or if you do not want to write it, no need for this sign. Okay, and we can write it like this only. Fine. Now this will become finally what this will become, VAN minus VA dash N dash, and that is ZAA minus ZAN into IA, and then it will be ZAB minus ZAN into IB plus IC. Then finally it will become minus minus, it will become, we'll take ZNN outside, so that will become ZNN first into minus ZAN, that will be IA plus IB plus IC. So this is very clear. So we further will simplify it now for writing a final equation. So that will be VAN minus VA dash N dash. So we'll take IA common now. If we take IA common, then it will become ZA will come from here, ZNN will come from here, from A. Here from ZNN positive and negative will be only. One will be this ZAN. Okay, another will be this ZAN. So this will be 2 ZAN. That will become IA. Similarly, you can check ZAB plus ZNN, and similarly we are going to get minus 2 ZAN for IB. Simplifications. And last what we are going to get, ZAB plus ZNN, ZNN minus 2 ZAN for IC. So let's call this equation number 5. So we're getting, after simplifying, we're good. So we'll write other equations similarly. We don't have to evaluate them also. Similarly, what we are going to do, VBN minus VB dash N dash will be written as ZAB sorry, here it's a mistake. I think this should not be, yeah, it will be, because this A face, it will be ZA. Somewhere we should get here ZA, yeah, second term we'll get. So here it will be ZAB plus ZNN minus 2 ZAN, that will be with IA, but with phase B, what we are going to get, we are going to get ZAA plus, similarly here we are get ZA, we will get here also ZNN minus 2 ZAB into IB. Phase B we are, because we are talking about the phase B, so phase B will have self impedance. Phase A here will have self impedance. Plus will be the same thing, ZAB plus ZNN minus 2ZAN into IC. So that will be same. Now last equation is VCN minus VC dash N dash will be ZAB plus ZNN minus 2ZAN IA. So then we will have second will be ZAB plus ZNN minus 2ZAN into IB. Now third will have a change because we are talking about C. So self impedance will come into the picture. That is ZAA plus ZAA plus ZNN minus 2ZAN into IC. So this is the set of equations we are getting for 3. We'll add a page here. Okay. Now next, now what we'll have, we have a neutral conductor is present here that will change the self and mutual impedance of the phase conductors. So we can write the presence of neutral conductor changes the self and mutual impedance of phase conductors to, how it will change, let's see. So ZS, let us say ZS is the, what is this? This is the self impedance that is approximately equal to, you can see here, self impedance is approximately equal to ZAA plus ZNN minus 2ZN. Because how? Because in each phase we have seen that self impedance in that particular phase is equal to ZAA plus ZN plus 2ZN, that you have seen. Now what you have seen, mutual impedance written as Zm, that is approximately equal to ZAB, you can see from above equation also, plus ZNN minus 2ZAN. So we have seen that, you can see it very clearly. ZAB, ZNN minus 2. So mutual are this in phase C, self is this. Mutual are this and this in phase B, self is this. In phase A, self is this, mutual are other two. So very clearly I have written that in presence of neutral conductor, the values of the self and mutual impedances of the phase conductors can be written like this. This is very clear from the above equation. Now let's write set of equation 5. This all is a set of equation 5. So let me write it. This is all a set of equation 5. Okay. So set of equation 5 can be written in a matrix form, writing equation 5 in matrix form. Okay. Using above notations. Above notation means we will use this notation. Now for self, we will use this. For mutual, we will use this. That's the meaning of above notation. Now what we have this value. Sorry. Okay. So what we have, first value is VAN minus VA dash N dash. So we will write this. VAN minus VA dash N dash. And second we have VBN minus VB dash N dash. Third we have VCN minus VC dash N dash. We'll write this in matrix 4. Sorry. So we'll write this in the matrix form. Okay, this will be equal to, let me write it more precisely. Okay, this will be equal to, we will write VAN once VA dash N dash, that can be written as VA A dash. We'll notate it VA A dash, that will be VBB dash VCC dash. So that further will be equal to, that will be equal to, okay, make it to matrix first. Okay. So that will be equal to, now ZS will come first in phase A. We have seen that ZS, then will be ZM and ZM because we have given the notations to them. Second, first will be ZM in phase B, then will be ZS, and then will be again ZM. Phase C, it will be ZM, ZM, and it will be ZS very clearly. And currents on this side will be IA, and that will be IB, and that will be IC. Okay, so voltage drops across each phase are, we have written that above. So voltage drops across each phase conductors are, what are they? So VAA dash, we have written approximately equal to what? That is approximately equal to VAN minus VA dash N dash, and then VBB dash, we have written approximately equal to VBN minus VB dash N dash, and then VCC dash, we have written equal to VCN minus VC dash N dash. Let's call them, let's call it equation number 8 and call this matrix as equation number 7. Okay, so it's very clear from this self and mutual impedances. Now you can very clearly see from the equation number 7, it does not include the neutral conductor. That means when we will explicitly say, that means when we'll explain, when we are talking about this equation, it does not include the neutral conductor. And ZS and ZM can be regarded, these are the parameters. These are the parameters of what? These are parameters of the phase conductors alone. They are not having any mutual or self, without any self or mutual inductance. So these are the parameters of the phase conductor. So there is no mutual and self impedances, we can say, inductances associated with the return conductor. What we are talking about here, please, once again, I will explain. The equation 7th is very clearly, it includes the, in this case, it does not show any inclusion of the neutral conductor, or it does not explicitly explain about the inclusion of the neutral conductor. So what's that? ZSM, ZM, that means these two parameters can be regarded as the parameters of the phase conductors alone. So they will be a parameters of the phase conductors alone. So they will not be having any self or mutual inductance that is being associated with the return conductor. So it's a very clear thing. So we will write here ZS and ZM can be regarded as parameters of phase conductors alone. Okay, without any self or mutual inductance associated with the return conductor. Okay. Now, voltage drops and currents which we have can be written in terms of the symmetrical components. We know how can we can multiply by the we can multiply them with the matrix A, and that becomes the symmetrical components. So we'll write here voltage drops and currents can be written in terms of their symmetrical components, with phase A as reference phase. Okay, with phase A as reference phase, so that will be A multiplied by VAA dash 0, and then VAA dash 1, VAA dash 2. That will be equal to, you can see here, matrix. This is VAA dash, so we'll put them all in the sequence components. What we have to do, we have to multiply them with the matrix A. They will become symmetrical components that we have seen already. So that then matrix will be same, ZS, ZM and ZM. Then we will have ZM, then ZS and ZM. Then we will have ZM, ZM and ZS here. So that will be matrix, and currents again we will change them into the symmetrical components. So that will be IA0, IA1 and IA2. We have seen this equation when we have to change a phase currents or voltages into symmetrical components. So we have to multiply by the matrix A. We have proved it in the previous classes. So this is equation number 9 we have. Now let's try to solve this equation, because we need to multiply this both sides by A inverse, so that we will get any matrix multiplied by its inverse gives us unit matrix. Unit matrix multiplied by any other matrix will be the value of that matrix that I have already explained. Okay, pre-multiplying, or I will write it here. In order to solve it, equation 9 by A inverse, we get, let us see what we get. So I told you, any matrix multiplied by A multiplied by its inverse gives a unit matrix, and unit matrix multiplied by any other matrix gives the value of that matrix. So this is the way. So I'll be writing here the value simply of this matrix. A dash 1, A dash 2. Okay. So that should be equal to A inverse on this side. Rest all the matrix will be same. Okay, let me write it. ZS, ZM, 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 sorry, ZS, ZM. Then we have ZM, ZM, ZS, and A matrix multiplied by the symmetrical value of the currents. So let's solve it now. Now this right hand side I'm writing here, right hand side will be inverse is 1 by 3. We have seen that value. 1, 1, 1, 1, 1 here, A square, and this will be A square A. That is multiplied by same matrix, that is ZS, ZM, ZM, and this will be ZM, ZS, ZM, that will be ZM, ZM, and ZS. A matrix is simply 1, 1, 1. This is 1 here, and this will be just opposite to this. This will be A square A, and this will be A square. Close it, and then we have symmetrical components. I0, I1, I2. Now, again, further simplifying this step, this further can be written as, we'll keep this A inverse as it is, 1, 1, 1, 1, 1, A square, A. Now we'll multiply each row. I will be writing the simple value. I will not be explaining. See, ZS first row with first column, ZS plus ZM plus ZM. So that will be ZS plus 2ZM. That will become first entry of this matrix. Next will be ZS plus A square ZM plus A ZM. Okay. Third entry will be ZS plus A ZM plus A square ZM. So that will continue for the others. So you can simply rows have to be multiplied with the columns. Sorry. Rows have to be multiplied by the columns. First column, it will become first entry. Second column, second entry of the first row. Third. So that you know. So I'll be just writing it. It will become a big matrix. So first will be ZS plus 2ZM entry. Second will be ZS plus A square ZM plus A ZM. Third entry will be ZS plus A ZM plus A square ZM. Okay, that will be third entry. Okay, that will be third element of this row. Second row will be similarly, you can see second row, 2ZM plus ZS, and then it will be ZM plus A square ZS plus A ZM, then ZM plus A ZS plus A square ZM. Last will be again same, 2ZM plus ZS, and that will be ZM plus A square ZM plus A ZS. Then last will be ZM plus A ZM plus A square ZS, and this last column will be as it is, A1, A2. So that's the last column we have. Oh, sorry. So that's the last column I'm writing. Okay. Now, you can see this ZS plus 2ZM here. Okay. This 1 plus a square. We can take it common, and yeah, we can leave it and we can further multiply it by 1 by 3. And then if you calculate this, again, it will become first row will become, first element of the row will become, so row will be multiplied by ZS, and that will come 3ZS plus 6ZM. So divided by 3, that will be ZS plus 2ZM. So first entry here will become, that will become in this column finally. You just have to multiply it. Here it is ZS, 3 are ZS. So divide by 3, it will be ZS. Okay, plus 2ZM. Now let's have a look at the second entry. So second will be, all together have to be added with this 3 elements of this multiply this column. So 1 by 1. So ZS will be how many? ZS will be ZS common into 1 plus a square, that will be 0. So ZS will become 0. Now let us see at ZM, 1 ZM. ZM will be 1 plus, here you can see, ZM will be here 1 plus a square, again 0. And third ZM will be again 1 plus a square, again 0. So I will, this all mutual, wherever this column, this will become 0. So here it will become 0. So this will become ZM, ZS minus ZM. This will become 0. This will become 0. This will become 0. This will become 0. And finally, because we will be using this identity, a 1 plus a square is 0. Because of this, we will get the results. So on this column, it will be IA naught, IA1 and IA2 on this side. So from here, we can conclude that positive, negative, and 0 secants. Oh, sorry, it's not 0, third column. It is ZS minus ZM. Positive, negative, and 0 secants impedances are how we can write them. So 0 secants will be ZS plus 2ZM. See, 0 secants is corresponding to this. Then positive secants will be ZS minus ZM. And negative secants can be ZS minus ZM. Okay. So VA A dash 0 will be VAN 0 minus VA dash N dash 0. We have seen this identity previously also. So that is equal to nothing but ZA Z naught I naught. Similarly, VAA dash 1 will be VAN1 minus VA dash N dash 1, that will be Z1IA1. Similarly, VAA dash 2, that will be VAN2 minus VA dash N dash 2, that will be Z2IA2. That's a negative secants component of the voltage. So this is 11 equation. So this values you have to remember, impedances you have to remember, what will be the 0 secants impedance, positive secants and negative secants, what will be the 0 secants current, positive secants, voltage, 0 secants voltage, positive secants and negative secants voltage. That will be simply multiplied by their impedances. Okay. So this was the first part of this. Next topic which we have. Any questions regarding this, Sana?
No, sir.
Why is coming this guy late? Any questions regarding this? Okay, let's move further. Next topic which we have today is sequence circuits of star delta transformers. just basics what I have explained till now, you should know that. And then, so we have next topic as sequence circuits of star delta transformers. This is also an important topic. So I have drawn some diagrams. I will be explaining these diagrams afterwards. These are very simple diagrams. But before that, I will give some brief introduction about this. What we are talking about this topic. What the topic says itself. Okay, we are talking about the sequence circuits. So positive, basically, when we are talking about sequence circuits, it will be positive, negative, and zero sequence circuits. Now, the sequence circuits of three-phase transformer depend upon what? They depend upon the connections of primary and secondary side. That means on the primary and secondary side winding, what are the types of connections we have? That will depend on them. That's the first thing. So, sequence circuits of three-phase transformers depend on they will depend on the connections on primary and secondary windings. Because we are having three-phase transformers, it can be star, 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 delta, 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 star, star, star connected, neutral grounded, star connected, impedance grounded. So it can be any type of connection. We will see that one by one. We will taking that table we will take separately. Then different connections of star and delta windings will determine the configurations of the zero sequence. Zero sequence is very important for us, zero sequence circuits. And phase shifts in the positive, negative, and zero sequence circuits. So different combinations will be there, and that will determine the configuration. So there will be different combination. That means it can be star, delta, star, star, star on primary sides, star on secondary sides, delta on primary side. Any combinations can be there. So the different combinations of delta and star windings will determine the configurations of what? Zero sequence circuits. And phase shifts also. And phase shifts. So we'll see phase shift, how much will be there in the positive, negative, and zero sequence circuits. So that's also important. So we have a combination that will determine the configuration that we will see. And if there will be a phase shift, how much that will be, we'll see that later on. We know this, that no current flows in the primary of the transformer. No current will flow in the primary of the transformer unless current flows in the secondary. So neglecting other, we can neglect the magnetizing circuit is very small. We have already talked about it number of times. So we can neglect that. So that point we already know. The current in secondary will flow once the current in primary, and there will be no current in the primary if there is no current in the secondary. So next we know that we also know primary current is determined by what? Primary current is determined by the secondary current, and that will depend on the turn ratio. So primary current is determined how? It is determined by secondary current. That means we should know what is the secondary current, then we can find the value of primary current. And also we should know the turn ratio. Also we should be knowing the turn ratio of windings. And we can neglect all, we know that magnetizing circuit we can later on neglect. There are 5 possible combinations, and there are lots of combinations. 5 possible are main combinations along with their zero sequence circuits that will be shown later on, that I will show you. Now in this case, if I will talk about the arrow, okay, the arrow on the connection will show what? The arrow on the connection, yeah, on the diagram which will be drawing it, that will indicate the possible paths of the flow of zero sequence currents. So the arrow on the connections show the possible path of flow of zero sequence current. So whenever I will draw the arrow, that will show where the zero sequence currents are flowing. So the arrow on the connection, and write a connection diagram, shows the possible paths of the, that's all. Now if the arrow will not be there, the absence of an arrow indicates that transformer, that will indicate what? The transformer connection is such that zero sequence currents cannot flow. So whenever there will be no arrow, absence of arrow indicates that the transformer connection is such that indicates that the transformer connection, the arrow is such that the transfer connection is such that zero sequence currents cannot flow. So it should be very clear. Arrow will show the path where the zero sequence current will flow. Very simple. And if the absence of arrow is there, that will indicate that there is no path for zero sequence currents to flow. This type of connection we'll be having. The zero sequence equivalent circuits, they are approximate. They're not 100%, you can say, appropriate circuits. The zero sequence equivalent circuits are approximate. They are approximate, not 100% appropriate, as they will be shown. I'll show them as shown. Since what? Why they are approximate? Because resistance and magnetizing path that we have talked already, resistance and the magnetizing current path are neglected from the circuit. So because approximate word will be using, why? Because approximate, because these two we are not including. So it will not be 100% appropriate or precise. So we'll continue with the next class and we'll take case 1, where I will give you the complete summary of that case. Then other cases you can yourself do and I will give later on the summary also. I will explain the one case in detail like this, how we will take these circuits, and we will inshallah continue in the next class. Anji, beta Sana, is there any questions regarding today's lecture?
No, sir. No, sir.
Anybody has a question? Okay, we can stop the recording here.